Okay. Calculating values to this continued fraction is quite simple. We'll just use this equation, and this is the Rogers Ramanujan continued fraction. So we'll use the Rogers Ramanujan continued fraction, and the value we need is r of e to the minus 2 pi. And we'll use a formula for this. So we know that the golden ratio plus r of e minus 2 alpha times the golden ratio plus r of e minus 2 beta equals square root of 5 of the golden ratio. And we'll multiply these out, and a times alpha times beta equals pi squared. So we'll just use pi for both. So we'll get golden ratio squared plus r of e minus 2 pi squared plus 2 golden ratio r of e minus 2 pi equals square root of 5 over the golden ratio. Okay, this is understandable, I'm guessing, and we'll just plug in a variable x equals r of e minus 2 pi, and we'll get a quadratic equation which we can solve. So this is the x term, this is the free term, so we'll just get x equals minus 2 the golden ratio plus or minus, we'll have to disregard the minus term and just use the plus term, because it's not defined. The minus term is not defined, so we'll just get 4 golden ratio squared minus 4 golden ratio squared minus square root of 5 golden ratio, and we can this is over 2. Now we use the quadratic equation. This is understandable, and we'll get minus 2 golden ratio plus or minus. We'll take a common factor of 4 golden ratio. Actually, they cancel out. There's a minus sign, and we'll get we'll take the 4 as a common factor, and it will become a 2, and it will cancel the 2 here. So this will all cancel, and we'll just get square root of 5 golden ratio, and we'll disregard the negative term. So we'll get that the answer is square root of 5 times the square root of the golden ratio minus the golden ratio. And now we have a value for this fraction. So we know that this fraction equals square root of 5, the golden ratio minus the golden ratio. And I'll remind you that the golden ratio is 1 plus square root of 5 over 2. Okay. I feel like continued fractions are quite interesting, at least the Rogers Ramanujan continued fractions, because it involves a lot of advanced mathematics and really abstract mathematics. So yeah, I would love to maybe do Otto values as well. You could do Otto values. There's an Otto formula which involves a alpha and beta equals pi square over 5, so you can just repeatedly use this formula, both formulas, to get more convoluted values. But this is a great way to do it. Okay, bye.